Hello and welcome to the Polymath REU for the summer of 2020. We're excited to have you. My name is Abigail, and along with Pat and Erin, I will be one of the mentors for the Explore Director Game project as well as the Hat Matching Game project. So today we're going to talk about, in this video, the Explore Director game, but there will also be a lot of information on the Hat Matching game elsewhere, so I encourage you to take a look at that as well. So before we talk about what this project is specifically, we should just go over a little bit of background that you might want to have before starting this project. So what is the necessary background? The good news for this project is that it's pretty simple. We just need a little bit of graph theory. So some basic graph theory. And the even better news is that even if you haven't seen graph theory before, it's not too hard to pick up. And we'll be posting some resources on the wiki, so you can read through those on your own. You can always come and ask us questions. And I promise you, even if you haven't seen it before, we'll be able to get you up to speed pretty fast. All right, so just so we know what we're talking about for this video, well, what is a graph? We're going to have vertices, they're also sometimes called nodes, and edges. All right, and so it's something, we've got some dots, these are going to be our vertices, and then maybe we've got some edges between them, maybe something like that. And for our purposes, we're not going to allow any loops, any edges that start and end at the same vertex. And between two vertices, we're going to allow at most one edge, so no multiple edges. And we'll be thinking about connected graphs, and you'll see why for this. It's not going to make much sense if they're not connected. All right. And I will also say that if you check out our wiki page, you'll notice that there are some papers in there and in the introductory document which talk about some applications and variants in algebra and in theoretical computer science. And so what I'll say about that is that if you have seen some of those things before and you're interested in it, feel free to go and check that out. But it's not going to be the focus this summer. And so if you have no background in abstract algebra or in any theoretical computer science, don't worry. We're probably not going to spend much time going there unless there's a lot of people who really want to think about that stuff. Okay, so now that we've gotten the background out of the way, let's talk a little bit about what our project does. So it's called the Explore Director game. So we should probably say what the game is and who these two people are. All right, so we're going to start with a graph. This is going to be our game board, essentially. Okay, and a token on one of the vertices. Token on a vertex. That's going to be the one game piece. So we've got our board, we've got our game piece. Now we have two players in this game. So we've got the explorer and the director. And what the explorer is going to do is the explorer will pick a distance. So we'll pick a number. Right? Picks a distance. And then the director will pick a specific vertex that's that distance away. All right, so picks a vertex that distance away to move the token, and moves the token there. All right, so we have these two phases. The explorer is never actually going to touch the token. The explorer, they just pick a distance, and then the director says, all right, you've picked that distance, now I'll pick a vertex that distance away and move the token. All right, so what's the goal of the game? The explorer wants to maximize the number of vertices visited. All right, wants to maximize the number of vertices visited. And you can think of this as you just kind of keep playing the game as long as they want to be playing the game, all right, and until both of them agree to stop. Vertices. And well, if I say that, I bet you can guess what the director wants to do. The director wants to minimize. Wants to minimize. Okay. And now, well, bet you can anticipate this next question, right? What is the optimal, if both players play optimally, how many vertices are going to be visited? So we're going to define this value f star of g to be the number of vertices visited if both players play optimally. Number of vertices visited if both players play optimally. All right, and we're going to ask ourselves, well, what is f star of g for different graphs? So before we get into that, let's just play the game on one small example really quickly, just to make sure we're all on board with what this game is. So I'm going to pick g to be this graph that we're going to call C4, and what is that? It's the cycle graph on 4 vertices. So you draw 4 vertices and you go around in a cycle. All right. Hopefully, even if you haven't seen it before, you believe that that looks like a cycle. All right, and now in this particular case, all the vertices kind of look the same, so it doesn't really matter what vertex I start at. But let's say the token starts here. All right. Token is that little blue vertex. Okay, now let's say I'm the director, and so this is position 1. And so first I'm going to play the role, explorer goes first. So first I'll play the role of the explorer. And I'm going to say I want to move to a vertex distance 1 apart. All right, maybe I could say that. So I'll say distance 1. And now the director has 2 choices because there are 2 vertices distance 1 apart, that top left vertex and the bottom right vertex. And maybe the director's gonna pick the top vertex. All right, so this is gonna be position 2. So far, 2 vertices have been hit, okay? Now you'll notice that if the explorer now says distance 1 again, the director can just put the token back where it started, and the explorer hasn't gotten anything out of that. So that wouldn't really be playing optimally. But what if the explorer said distance 2? You'll notice that from that top left corner, there's only 1 vertex of distance 2 from it. It's the one in the bottom right. So if the explorer declares distance 2, then what do we get? The director says, well, there's only 1 place I can put you, so I'll just do that. I have no choice. All right, so that's going to be the 3rd position. Okay, let's just play this game out for 2 more steps. Now, again, if the explorer says distance 2 again, the token will just pop back to where it was in the previous step. And so nothing was gained by that. Now, if they say distance 1, the director could put them at that one last unseen vertex up in the top right, or could just put them back at the vertex it started. But, you know, it's better than guaranteed no gain, so I'll say distance 1. But if I'm now putting on my director hat and trying to play optimally, I'm going to put the token back where it started, right? 'Cause I'm trying to minimize the number of new vertices we visit. So this is position 3. Position 4. But now we'll see that the explorer has won the game. They'll have visited all the vertices by now declaring distance 2, because then the vertex is going to be forced into that top corner. Okay. That's the only thing that the director can do, and so the game is over. Now, I want you to think a little bit about, did I play that game optimally for both sides? Was there something I could have done that would have made it quicker? Sit on that and see what comes to mind. And in this project, we're not going to be too concerned with how quickly we can get to F star, but it is something that's interesting to think about. All right, so I would recommend, right, start playing with some other small examples, right? So play the game on some small examples. If you have some people that you're at home with, roommates, siblings, parents, right? Teach them the game, get them to play with you, see how it goes. Okay, so maybe we could think of a small path, let's say, maybe a really small path, just on 3 vertices. Maybe I could take that cycle graph I already had and just throw an extra edge in there. I don't know, pick your favorite small graph and start playing with it. Okay, so, well, we did this for a cycle of size 4. Now, what is known about this game? We didn't make this game up. This is a game that some mathematicians have thought about in the past. And the main theorem that's known is about cycles specifically. So it comes in 2 parts. The first deals with cycles whose length is a power of 2. So if n equals 2k, then f star of cn equals n. Okay, so this was like this example we did. 4 is obviously 2 squared, and we saw that yes, we could hit every vertex. Okay, and the second part says, well, if it's not a power of 2, then I can write it as p times m, where p is the smallest odd prime factor. Then n equals p minus 1 times n, oops, not n, f star. F star of g is, I guess I should specify, it's not just a g, it's cn, is p minus 1 times n over p. Or another way I could write this as n minus n over p. So another exercise, this theorem has been proved, but it's a really great idea when you're starting a new project to just kind of go through the results that are known and get a feeling for how they were proved and try to do it on your own. So try to prove 1, and I'll give you a hint, via induction. Right? So think about what you want to induct on and try to prove that first statement about these cycles whose length is a power of 2 via induction. And maybe for part 2, just try to prove the upper bound, that f star of cn is at most p minus 1 times n over p if n equals p, as in 2. Okay, so what does that mean to do that? Right, that means that there's some strategy that the director can take where they will guarantee at least n over p vertices are never visited. Okay, so try to think of nice sets of size n over p and make a strategy that will always guarantee that the director can promise that those vertices are never had. All right, and if you want to learn a little bit more about the background, I strongly encourage you to go to our wiki. There's a little document there with some introduction. A lot of this stuff is there, and a little bit more detail. And of course, you can always ask us questions. So I'm just going to end with a little bit of, well, once you do that, what's next? What's the actual research project? Think about the main question is determine f star of g for other classes of graphs. Okay. Again, as I said before, you always want to start small. Start with some small examples, play around, see if you can figure out what f star of g is for those small examples, and then see if you can extend to full classes of graphs, whatever your favorite friendly class of graph is. All right, and things to think about just when you're considering this problem. Well, one thing I didn't really talk about, I kind of glossed over, is does it matter where we start? Okay, it could be that it's independent of that. It could be that it's not. It could depend on the graph. All right, so think about if it matters where we start. Another thing to think about is, what if we don't use distance? what if we alter our notion of distance? So in the problem as I defined it, I'm using the graph distance term, by which I mean it's the length of the shortest path between two vertices. That's the distance. But what if I didn't require the director to pick a vertex whose shortest path between that and the current spot was D, whatever the explorer said? What if they're just allowed to pick any path? So what if the director can move the token along any path of length D? Okay, so you start somewhere, the explorer declares some number D, and then the director can just go along any path of length D. It doesn't have to be to a vertex of distance D away. They might be taking the long way around. All right, does that change the answer? What if you do the same, but now consider a walk instead of a path? And if you haven't seen any graph theory before, a path just means you're not allowed to revisit any edges or vertices. So you can travel along, but you're not allowed to go backwards. In a walk, it's the most extreme version of being able to go backwards. You can revisit vertices, you can revisit edges, you revisit whatever you want. All right? Then what is the strategy here? And I will give you a little hint that this last one is a little bit of a silly question, and that the director has an awesome strategy for them that they can just keep using over and over and over again, and will make F star really, really small. Okay, so I think that's where we're going to end with for today. As I said, there's a lot of information up on the wiki already. There's an introductory document. I'll post these notes up there, and a bunch of papers. We're not expecting you to read them, but if you're curious, you can start to take a look at some of them just to see what a math paper looks like, even if you're not really going to read them. All right, we will be having a introductory meeting on Tuesday. If you are viewing this prior to Tuesday, I encourage you to come. And if you decide to participate in this project, we'll be meeting multiple times a week and rotating kind of through all the mentors. You can get a chance to talk to each of us. So I hope you enjoyed learning about all of these different projects, and good luck for the rest of the summer.